Welcome to my channel. Today I'll solve the problem 1.16 of Pathria, and this is the last problem of chapter 1. Let's read the problem. Establish thermodynamically the formulae that are given here. Express the pressure P of an ideal classical gas in terms of the variable mu and T and verify the above formula. So in problem 1.9 I have already showed this type of relation, and there we have used Euler identity. In spite of P, there was entropy S. You can see that. Okay, let's see the solution. So we have already proved the Euler identity in 1.9, and this is the equation in mu equal to E plus PV minus TS. Just we have to take derivative by taking one variable constant. We can prove these two given equation. Let's see one by one. So differentiating equation 1 with respect to t, keeping them constant. So you can see, and we just simply landed on our desired equation. Similarly, we have to differentiate equation 1 with respect to mu, keeping this constant. So we'll also land on the second desired equation. These are very straightforward calculation. Now from thermodynamics we know the relation G equal to mu n equal to A plus PV. Here G is the Gibbs free energy, A is the Helmholtz free energy. From that we can calculate the pressure, that is 1 by V multiplied with mu n minus A. Now in Pathria 1.5.8 you get the equation. So this is the entropy of gas mixing part, basically the Gibbs paradox problem. So they have calculated and also derived there. So I have not derived here. You can just see from there. We have to put this value in equation 4. So this is our desired pressure equation. Here variables are only mu and T. So the equation 5 is the Helmholtz free energy for ideal classical gas, and this is for indistinguishable because when we are dealing with the entropy of gas mixing and the Gibbs paradox problem, so there we have to consider the classical gas as indistinguishable to solve the Gibbs paradox. That's why we have taken here the indistinguishable gas. So there they have actually calculated the entropy first, and from the entropy they have calculated the Gibbs, the Helmholtz free energy. So now it's time to verify the result. So this is the left hand side. Just put the value of P here, and these are the mathematical steps. You will get this equation, and if you compare with the equation 1.5.1a, this is the actual that entropy equation they have derived. So this is basically same as S. And in the second part, this is very straightforward. You can directly obtain it. So both results are verified. Thank you.